Imagine for a moment the quiet hum of your refrigerator or, that blast of your air conditioner on a really hot day. We rely on these things constantly, don't we? Keeping food fresh, homes comfortable, our lives cool.
We absolutely do.
But have you ever stopped to think about how much energy all that cooling actually uses? It's probably a lot more than you might realize.
It's a staggering amount, really. Global energy demand is climbing fast, and a huge chunk of that, a really significant portion, is, well, it's eaten up by refrigeration and air conditioning.
And the refrigerants themselves are a problem too, right?
That's the other big concern, yes. Many traditional systems still use these harmful fluid refrigerants like hydrofluorocarbons, HFCs, and these things contribute massively to greenhouse gas emissions. It's a problem we really need to tackle.
Right. And that's exactly why we're doing this deep dive today. We're looking at a pretty surprising solution: magnetic refrigeration. Our sources are calling it a highly promising and sustainable solution, something that could revolutionize thermal management.
Sounds almost like sci-fi, but it's real.
Oh, it's very real. And it certainly has the potential. Our mission here is to unpack the science behind it, how it works.
And where it came from.
Exactly. Trace its history, look at where it might be heading, and really understand how it could give us a cleaner, quieter, and much more efficient way to cool things down. We've gone through a stack of sources,
Yeah.
and we're aiming to distill the key insights for you, give you that shortcut to understanding this, well, potentially groundbreaking tech.
Okay, let's unpack it then. At the heart of magnetic refrigeration is something called the magnetocaloric effect, or MCE.
Ah.
You described it as like a hidden superpower in some materials. So what exactly is this phenomenon? How does it work? It's magic.
So the magnetocaloric effect, it's a magnetothermodynamic thing. Okay, imagine a material, right? And it's like it has tiny internal magnets, spins, we call them. When you bring an external magnet close, you apply a magnetic field.
That field forces those little internal spins to line up, to get ordered. Now, if you do this quickly, so no heat can leak in or out, that's what we call adiabatic conditions, all that energy from ordering the spins, it has to go somewhere.
It heats up the material.
Exactly. It gets converted into heat, vibrational energy in the material structure, its lattice. So apply the field adiabatically, the material gets warmer.
Okay, so field on, it gets warm. How do you get the cooling effect then? That's the goal, right?
For cooling, you reverse it. You adiabatically remove the magnetic field, those spins that were lined up. They relax, they become disordered again, they gain magnetic entropy or messiness.
Ah,
And to balance that energy change internally, again, if no heat can get in, the material has to cool itself down. It sucks heat out of its own lattice structure. So remove the field adiabatically, the material gets colder. That's the cooling effect.
and you mentioned temperature change and entropy change. Are they sort of two sides of the same coin, or is one more important for, like, building a fridge?
They definitely go hand in hand, but we measure them in two key ways. First, there's the adiabatic temperature change, a TAD. That's the straightforward one. It's literally how much colder the material gets when you pull the magnet away, assuming no heat leaks in. That's your direct cooling power.
Got it.
Second, there's the isothermal magnetic entropy change, ASM. This is a bit more abstract. It measures how much the material's internal magnetic disorder changes when you apply or remove the field, but while keeping its temperature constant. Think of it as like the raw potential for cooling work stored in the magnetic alignment.
Okay, so ATAD is the cooling, ATAM is the potential.
Kind of, yeah. And while pretty much any magnetic material shows some MCE, what you need for practical devices is the giant magnetocaloric effect, GMCE. That's when these changes, ATAD and ESM, are big enough to actually be useful.
Giant is definitely the word you want if you're building something practical. This effect, it sounds fundamental. Did scientists figure this out recently, or has it been known for a while?
Oh, the journey is quite fascinating, actually. The very first observation goes way back to 1881. Emil Warburg noticed a tiny temperature change in iron when he magnetized it. Just a curiosity then.
1881, wow.
Yeah. Then, fast forward to 1917, Pierre Weiss and Auguste Piccard, they explicitly identified that it was reversible. You could heat it and cool it this way.
So they knew about it, but it wasn't immediately used for, like, keeping milk cold. Sounds like it stayed in the lab for a bit.
That's exactly right. For a long time, its main use was actually for getting things really cold. Like, unbelievably cold.
Right.
In the late 1920s, scientists like William Jock and Peter Dubby independently came up with adiabatic demagnetization refrigeration, or ADR.
ADR.
Yeah, it uses this effect to reach temperatures way below 1 Kelvin. Think fractions of a degree above absolute zero. Essential for some very advanced science, but, not exactly practical for your kitchen.
Okay, so super cold science stuff. But you mentioned gadolinium earlier, the GMCE discovery. When did people start thinking, hey, maybe this could cool our refrigerators?
That big shift, that revolutionary moment, really started in 1976. G.V. Brown, working at NASA Ames Research Center, discovered this giant effect in the element gadolinium, Clyde.
Near room temperature.
Exactly. That was the key. He built the first magnetic refrigerator prototype that worked near room temperature. That discovery, our sources say, kicked off a robust race for the best magnetocaloric materials. People suddenly saw a potential for everyday cooling.
And then there was another big leap, almost like a second breakthrough.
Yes, what our sources call a second paradigm shift happened in 1997, also at Ames Lab. Carl Scheiner Jr. and Vitaly Pecharsky discovered an even bigger effect, a colossal MCE in some gadolinium alloys, specifically GD5 Site 2G24.
Colossal.
But it wasn't just that it was bigger. They figured out why. It was linked to something called a first-order magnetostructural transition. Basically, the material doesn't just change its magnetic state, its actual crystal structure changed at the same time.
So a double whammy, magnetically and structurally.
Precisely. And understanding that mechanism gave scientists a whole new strategy. Instead of just stumbling upon good materials, they could start designing them, looking specifically for materials with these coupled transitions. It was a huge step forward in materials discovery.
Okay, so we've got the what the effect and the when, the history, but let's dive deeper into the why. What's actually happening down at the atomic level inside these materials? How does just flicking a magnetic field on or off make them hot or cold?
Good question. It really boils down to entropy, which is basically a measure of disorder or randomness within the material. The total entropy in a magnetic solid has a few parts. There's lattice entropy from the atoms vibrating.
Like thermal energy.
Sort of, yeah. Then there's magnetic entropy from how ordered or disordered those tiny atomic magnetic moments, the spins, are, and a smaller bit from electronic entropy in metals. The MCE happens because you can shuffle entropy between the magnetic part and the lattice part.
Okay, so shuffling entropy. How does the field do the shuffling?
When you apply that magnetic field, it forces the magnetic spins to line up. They go from disordered to ordered. That means the magnetic entropy decreases.
All right, less messy.
Exactly. Now, if you do this adiabatically, no heat in or out, the total entropy has to stay constant. So if the magnetic entropy goes down, something else has to compensate. What happens is the lattice entropy also decreases to balance things out, which means the atomic vibrations slow down. Wait, no, I misspoke there. Let me rephrase.
Okay.
When the magnetic field aligns the spins, magnetic entropy decreases. In an adiabatic process, this energy has to go somewhere. It gets transferred to the lattice, increasing the vibrational energy, so lattice entropy increases, and the material's temperature goes up. Apologies for that confusion.
No problem.
Yeah.
So field on, magnetic order increases, magnetic entropy down, energy transfers to lattice vibrations up, temperature up. Got it. So for cooling.
Right. Conversely, remove the field adiabatically. The spins relax, become disordered again. Magnetic entropy increases. To balance that, the material draws energy from its lattice vibrations. So lattice entropy decreases, the vibrations slow down, and the material's temperature drops. That's the cooling. It's all about that interplay between magnetic order and lattice vibrations.
And you mentioned gadolinium has high magnetic entropy.
Yes. Its electronic structure gives it a high magnetic moment, meaning it has a lot of potential magnetic disorder, a high maximum magnetic entropy. That's part of why it shows a strong effect.
You also mentioned lattice entropy and this magnetoelastic coupling. How important is the actual physical structure changing? Is it just the spins flipping, or is the whole material doing a little dance?
The lattice is definitely doing a dance, especially with those first-order transitions. Magnetoelastic coupling means the magnetic state and the lattice structure are linked. Change one, you affect the other. In these magnetostructural transitions, the change in lattice parameters is significant, and it involves a substantial amount of latent heat energy absorbed or released during the structural change itself. That latent heat contributes significantly to the giant effect.
But is there a downside to the lattice being involved?
Well, yes. If the material has a very high heat capacity, meaning it takes a lot of energy to change its temperature, that can actually dampen the temperature change 8 ATAD, the lattice can sort of soak up some of the effect.
And the electronic part? Still minor.
Generally, yes. Electronic entropy contribution is usually much smaller, mostly relevant in metals through something called the Zeeman effect. We usually focus on the magnetic and lattice parts for MCE.
Okay, this leads perfectly into a really crucial point you touched on. The type of phase transition matters. Second order versus first order. What's the key difference? And why is it so important for getting that giant effect?
It's hugely important for the size of the effect. Second-order phase transitions, or SOPTs, are gradual, continuous changes. Think about heating a typical ferromagnet like iron. It gradually loses its magnetism as you approach its Curie temperature. There's no sudden jump, no latent heat involved.
Like gadolinium?
Exactly. Gadolinium near room temperature is the classic example. It shows a nice, broad, symmetrical peak in its entropy change, ASM, around its transition temperature. Good, but not giant.
So first order is where the fireworks happen. That's the giant effect.
That's right. First-order phase transitions, or FOPTs, are abrupt, discontinuous changes. Think ice melting into water, a sudden change at a specific temperature involving latent heat. In magnetic materials, these FOPTs, especially the magnetostructural ones, where both magnetism and structure change abruptly, release or absorb a lot more entropy over a very narrow temperature range, resulting in a very large and sharp peak in both ESM and ATAD. That's the signature of the giant magnetocaloric effect, or GMCE. It's a much stronger effect, concentrated right around that transition temperature.
That sounds perfect. Why wouldn't we just use first order materials for everything then? Is there a catch?
Ah, yes. There's always a catch, isn't there? The big downside with FOPT materials is often hysteresis, both thermal and magnetic hysteresis. Think of it like friction or stickiness in the transition.
Yeah.
Meaning when you apply the field, the material doesn't respond instantly or fully, and when you remove it, it doesn't snap back perfectly either. There's a lag. This lag, this hysteresis loop, represents energy that's lost as heat in every single cooling cycle.
So it reduces the actual usable cooling effect.
Precisely. It lowers the overall efficiency of the refrigeration cycle. So you get this potentially huge peak effect, but the hysteresis eats into how much of that you can actually use effectively. It's a major challenge researchers are trying to overcome, getting that giant effect without the sticky hysteresis.
Okay, so define these materials, optimize them, understand the hysteresis. Scientists need ways to measure all this accurately. It sounds like pretty detailed detective work. What kind of tools are in their toolkit for characterizing MCE?
You're spot on. It's definitely detective work. And accurate measurements are absolutely essential. First off, though, even before measuring, preparing the material itself is critical. Things like arc melting or melt spinning are used to synthesize them, and the microstructure grain size, how uniform it is, that really affects performance. It's not just the chemical formula, but how it's put together.
Right. So once you have the sample, how do you measure the effect? Can you just stick a thermometer on it and watch the temperature change when you bring a magnet nearby?
Pretty much. That's the basis of direct measurement, using something called adiabatic demagnetization calorimetry. You carefully isolate the sample thermally, then rapidly change the magnetic field and measure the temperature change, ATAD, directly.
That sounds like the most straightforward way.
It is, conceptually. It gives you a direct measure of the cooling potential under ideal conditions. But it's tricky in practice.
How?
Well, achieving perfect thermal isolation true adiabatic conditions is really hard. Heat always wants to leak in or out. Plus, if your sample is metallic, rapidly changing the magnetic field can induce electrical currents within it, called eddy currents.
And those currents generate heat.
Exactly. Eddy current heating can counteract the cooling effect you're trying to measure, messing up the results. It's also quite slow to get good, reliable data this way.
Okay, so direct measurement's tricky. What about testing a material more like how it would work in an actual device, like a mini fridge setup?
Yes, that's definitely done. It's called active magnetic regenerator, or AMR, system characterization. Here, you build a small-scale prototype. You pack the magnetocaloric material into a bed, called a regenerator, pump a fluid through it, and cycle the magnetic field.
So you're mimicking the real process.
Precisely. It's much more complex to build and run, but it gives you real-world performance data, actual cooling power, the temperature difference it can sustain, efficiency under operating conditions. It tells you how the material really behaves in a system.
Makes sense. Now, besides directly measuring temperature or building a mini fridge, can you figure out the cooling potential from, say, just its magnetic properties, infer the effect?
Absolutely. That's where indirect measurement techniques are very useful. A primary method involves magnetization measurements. You measure how the material's magnetization changes as you vary the magnetic field strength at different constant temperatures.
Okay, how does magnetization tell you about cooling?
There's a fundamental thermodynamic relationship called the Maxwell relation. It connects the change in magnetization with field to the change in entropy. So from those magnetization curves, you can mathematically calculate the isothermal magnetic entropy change, ASM.
Clever. What are the pros and cons of doing it that way versus the direct temperature measurement?
The big advantage is you get a lot of fundamental thermodynamic information, and it's less sensitive to heat leaks than direct calorimetry. But there's a crucial catch, especially with those first-order materials.
Hysteresis again.
Hysteresis again. The Maxwell relation assumes the process is perfectly reversible, but hysteresis means it's not reversible. Using the standard Maxwell calculation on data with significant hysteresis can lead to a serious overestimation of the useful ESM. You calculate a big number, but it doesn't reflect the actual reversible cooling potential because of those energy losses. Plus, it involves approximations.
So magnetization data needs careful interpretation. You mentioned heat capacity earlier, too. Is measuring that important?
Yes, heat capacity measurements are also vital. Specific heat capacity, CP, tells you how much energy it takes to change the material's temperature. You need this value to accurately calculate the adiabatic temperature change, ETED, from the entropy change, ESM, that you got indirectly.
Okay, so ESM from magnetism, CP from heat capacity, put them together to estimate ETED.
Exactly. It gives you another way to estimate the cooling performance. Measuring CP provides crucial thermal data. But like the others, it can be time-consuming and needs to be done carefully for accuracy. It's all about building a complete thermal picture.
It really sounds like you need a whole suite of tools, like a full diagnostic workup for these materials, not just one single test. Are there other techniques besides these core MCE ones?
Oh, definitely. For a truly holistic view, scientists use lots of other techniques. X-ray diffraction, XRD, tells you about the crystal structure, how the atoms are arranged. Scanning electron microscopy, SEM, lets you see the microstructure, the grains and shapes. Differential thermal analysis, DTA, helps pinpoint those transition temperatures accurately. Even neutron diffraction can be used to probe the magnetic structure directly. It all feeds into understanding why the material behaves the way it does.
Okay, so you gather all this data, direct, indirect, structural, thermal. What are the ultimate bottom line numbers, the key performance parameters that tell an engineer, yes, this material is promising for a cooling device?
Right, boiling it down. There are a few key metrics. First, that isothermal magnetic entropy change, IRSM, we talked about. It's the fundamental measure of the MCE strength. For that giant effect, you're looking for values often above, say, 10 joules per kilogram per Kelvin for a decent magnetic field change, like 2 Tesla.
And the one that tells you how cold it actually gets.
That's the adiabatic temperature change. It's the most practical indicator of direct cooling capability. For room temperature stuff, you'd ideally want something better than maybe 2 Kelvin temperature drop for a 1 Tesla field change. That's a pretty good target.
Okay, this next one seems really important for real-world use. How do you combine the strength of the effect with how wide a temperature range it works over? Because a huge effect over just 1 degree isn't that useful, is it?
Exactly. That's where relative cooling power, RCP, comes in, and it's super important for practical applications. RCP essentially quantifies the total amount of heat the material can pump in one cycle across its useful temperature range. It combines the peak entropy change, Smax M, with the width of the temperature range over which the effect is strong, often measured as the full width at half maximum of the RSM peak TF EVU OCHM.
So higher RCP is better.
Much better. A higher RTP means the material can effectively pump more heat over a broader temperature span. That makes it much more suitable for building an actual refrigerator that needs to operate across a significant temperature difference. It's a really key figure of merit.
And I think I saw refrigerant capacity, RC, mentioned too. Similar idea.
Yes, very similar concept to RCP, also aiming to quantify the total heat transferable. Both RCP and RC give engineers a good measure of how much oomph a material has for practical heat pumping, especially when designing those AMR cycles.
Okay, great. So now we've got the science, the history, the measurements.
Yeah.
Let's talk about magnetic refrigeration in action. How do these things actually work? Forget the lab. Why does the fridge of the future get cold?
Well, fundamentally, it uses the magnetocaloric effect in a thermodynamic cycle. It's similar in principle to your standard fridge, which cycles a refrigerant using pressure changes. Here, we cycle a magnetic material using magnetic field changes.
Okay, so what's the ideal cycle? I think you mentioned a magnetic Carnot cycle. Walk us through the steps.
Right. The Carnot cycle is the theoretical ideal, the most efficient possible. It has 4 steps. First, isothermal magnetization. The MCE material is connected to the hot side, like the room air. You apply the magnetic field. The material wants to heat up, but because it's connected to the hot reservoir, it dumps that heat out at a constant temperature.
Okay, so it gets magnetized and pushes heat out in the room. Then the cooling part.
Step 2, adiabatic demagnetization. You disconnect the material from the hot side so it's isolated. Then you remove the magnetic field, as we discussed. Removing the field makes the material cool down. Since it's isolated, its temperature drops significantly.
That's where the cold comes from.
Yes.
And then it has to absorb heat from the thing you want to cool.
Exactly. Step 3, isothermal demagnetization. Now, the cold material is connected to the cold side inside the fridge. You might remove the field further or just let it sit there. As it naturally wants to warm up slightly, or its entropy wants to increase, it absorbs heat from the cold space, again at constant low temperature. This is the step that actually cools your food.
Makes sense. And the last step is just getting it ready to start over.
Yep. Step 4, adiabatic magnetization. Disconnect from the cold side, isolate it again, reapply the magnetic field. As the spins align, the material heats back up to the original hot temperature, ready to connect to the hot reservoir and start the cycle again.
That's the ideal cycle. But you said in practice they use something called the active magnetic regenerative refrigeration, AMRR cycle. Why the change? Is the Carnot cycle not practical?
The Carnot cycle is hard to implement perfectly, and the AMRR cycle is much more effective for achieving larger temperature spans with real materials. It's the real workhorse. Almost all practical magnetic prototypes use AMRR.
How does AMR work differently to get that bigger temperature difference?
The key idea in AMR is using the magnetocaloric material itself not just as the refrigerant, but also as a regenerator. Think of it like a thermal sponge. You have a bed of the MCE material and you pump a heat transfer fluid like water or helium gas back and forth through it while also cycling the magnetic field on and off.
Okay, back and forth fluid. How does that help?
It creates a temperature gradient within the bed. Here's roughly how it works. First, magnetization and hot blow. The regenerator bed moves into the high magnetic field. The material heats up. At the same time, you pump cold fluid from the cold end towards the hot end. This fluid picks up the heat released by the material and carries it out to the hot heat exchanger.
Okay, heat out, then.
Then, demagnetization and cold blow. The bed moves out of the magnetic field. The material cools down. Now, you reverse the fluid flow, pumping warm fluid from the hot end towards the cold end. This fluid gets cooled down by the cold MCE material and then flows to the cold heat exchanger to absorb heat from the space you're cooling.
Ah, I see. So the fluid flowing through the cycling material kind of cascades the cooling effect along the bed.
Exactly. It builds up a temperature difference across the regenerator bed that can be much larger than the ATAT of the material itself. It's a clever way to amplify the cooling effect.
So if we were to look inside one of these magnetic fridges, what are the main parts? What does it actually consist of?
Well, you've got several key components. The absolute heart of it is the magnetocaloric regenerator. That's the bed or matrix made of the MCE material. Designing this is crucial. The material might be particles, thin plates, porous foams.
You mentioned multiple materials.
Yes. Often for wider temperature spans, they'll use layers of different MCE materials, each optimized for a part of the temperature range. You also need good thermal conductivity within the bed, and it has to be mechanically strong enough to handle the fluid flow and cycling.
Okay, the heart. What about the muscle, the magnetic field source?
Oh, right, the magnetic field source. This is often the trickiest and most expensive part. You have a few options. Permanent magnets are attractive because they don't need power or cooling themselves. They're often arranged in clever ways, like Halbach arrays, to focus and maximize the field.
Right.
But their field strength is limited, maybe 1 to 2 Tesla typically, and you usually need to physically move the magnet assembly or the regenerator bed to cycle the field, which adds mechanical complexity.
What about electromagnets?
Electromagnets let you change the field strength electronically. No moving parts needed for the field itself. But they consume a lot of power, generate significant waste heat that needs managing, and can be bulky.
And the super high-tech option.
Superconducting magnets. They can generate very strong fields, like 5 Tesla or more, which boosts the MCE effect. But the huge drawback is they need to be cooled to extremely low temperatures themselves, usually with liquid helium, which adds enormous complexity and cost. So it's always a trade-off between field strength, cost, power consumption, and system complexity.
Okay, regenerator, magnet. What else is essential?
You need heat exchangers, one on the hot side to reject heat to the environment, and one on the cold side to absorb heat from the space being cooled. They need to be efficient, high surface area. And of course, you need a fluid pumping system to circulate that heat transfer fluid, water, brine, helium, whatever it is, reliably and efficiently through the regenerator and heat exchangers.
So it's definitely a system with several interacting parts. But the advantages you mentioned earlier sound amazing. Environmental friendliness, efficiency. Are they really that compelling? It sounds almost too good to be true sometimes.
They really are compelling, though. Like any technology, it's not magic. But let's focus on the upsides. The biggest one, truly, is environmental friendliness.
Right.
This technology completely eliminates the need for those harmful HFCs or CFCs used in traditional systems.
Which have high global warming potential.
Exactly, and ozone depletion potential for the older ones. Magnetic refrigeration uses benign fluids, water, brine, helium gas. They're non-toxic, non-flammable. There are zero direct greenhouse gas emissions from refrigerant leakage, which is a huge problem with current systems.
And you mentioned efficiency, too.
Yes, potentially much higher energy efficiency. Those AMRR cycles can theoretically reach efficiencies closer to the ideal Carnot limit than vapor compression cycles, especially over smaller temperature differences. We're talking potential energy savings of maybe 30%. Some sources even suggest up to 50% compared to current tech in certain scenarios.
Wow, 30–50% better efficiency.
Mm-hmm.
That's massive on a global scale.
It really is. Plus, because it's mostly solid-state operation, no compressor thumping away, you get much lower noise and vibration. Imagine a truly silent refrigerator or air conditioner, and potentially improved reliability because there are fewer moving parts subject to wear and tear, especially compared to a compressor.
A silent, efficient, reliable, eco-friendly fridge. That's the dream, isn't it?
Yeah.
Are there other benefits, maybe for more specialized uses?
Definitely. For cryogenic applications, it offers compactness and can achieve cryogen-free operation down to very low temperatures without needing liquid helium, which is becoming increasingly expensive and scarce. It's also inherently scalable, from tiny coolers perhaps for electronics up to large industrial systems. And the use of safe fluids enhances safety.
So where are we most likely to see this tech breakthrough first?
Mm-hmm.
What applications are closest to reality?
Well, the biggest potential impact, and where a lot of focus has been, is domestic appliances. Refrigerators, air conditioners, they account for such a huge slice of residential energy use. And the environmental pressure to replace HFCs is strong. Companies like GE built prototypes years ago showing it's feasible.
So maybe our next fridge could be magnetic. What about stores and businesses?
Commercial applications are also very promising. Think beverage coolers, supermarket display cases. Quieter operation is a plus there, along with the efficiency and green credentials.
And bigger scale? Industry.
Yes, industrial cooling and freezing. Food processing, chemical plants, maybe even data centers. The potential for significant energy savings, maybe up to 30% increase in efficiency sources suggest, and precise temperature control are very attractive in those sectors.
What about the really high-tech end? Space, science, medical?
It's already making inroads there. Cryogenic uses are well established, using ADR for ultra-low temps. Now, AMRR is pushing into sophisticated cryocoolers for things like quantum computing, where low vibration is absolutely critical. Because vibrations mess up the qubits.
Exactly. And for sensitive instruments on space-based telescopes like the James Webb's MIR instrument, the reliability and low vibration are key. Also finding uses in MRI machines, cooling superconducting electronics, and gas liquefaction, maybe down to 20 Kelvin or so.
That's an incredible range, from fridges to quantum computers to space. Any other surprising applications?
Well, beyond cooling, the MCE is being explored for some niche medical research applications, using magnetic fields to guide drug-carrying magnetic particles to a specific target in the body, for example, or even using the heating effect and reverse magnetic hyperthermia to locally heat and destroy cancer cells. Still early days for those, but interesting.
And it's not just cooling, right? You can run the cycle backwards for heating.
Precisely. Flip the cycle around and you have a magnetic heat pump. Instead of absorbing heat from the cold side and dumping it on the hot side, you absorb heat from a cool source, like outside air or ground, and dump it into a warmer space, like your house or hot water tank. Potentially a very efficient way to do heating as well. Okay, this all sounds fantastic. Really revolutionary potential. So,
Yeah.
What's the holdup? Why isn't my fridge magnetic already? What are the big hurdles still standing in the way?
Yeah, that's the billion-dollar question, isn't it? There are definitely significant challenges falling into a few main categories. First and foremost are the material challenges.
Finding the perfect stuff.
Finding the good enough stuff, really. The primary goal is still optimizing MCE performance, getting materials with large NTSM and ETAD that work over a decent temperature range, and critically, that work well with low magnetic fields. Fields that you can realistically generate with affordable permanent magnets, not giant superconducting ones.
So good performance without needing a monster magnet.
Exactly. It's a tough combination to achieve, and even when you find materials with a large effect, especially those first-order ones,
Hysteresis bites you.
hysteresis bites you. Mitigating hysteresis losses is a massive hurdle. That energy lost in every cycle kills efficiency. So a lot of research goes into finding ways to reduce that stickiness, maybe through controlling the material's microstructure, using amorphous or nanocrystalline forms, or finding new compositions with inherently lower hysteresis.
And the cost of the materials themselves. You mentioned rare earths earlier.
Cost and abundance, absolutely. Gadolinium and other rare earths used in some top-performing materials are expensive, and their supply chains can be volatile. So there's a huge push towards finding effective MCE materials based on cheaper, more abundant elements. Think iron, manganese, silicon, phosphorus, boron, or at least significantly reducing the amount of rare earth needed.
Okay, so better, cheaper materials without hysteresis. What about making them last? Will my magnetic fridge work for 15 years?
That's the mechanical and chemical stability challenge. Many of these high-performance intermetallic compounds are unfortunately quite brittle. Hard to shape them into the thin plates or complex structures needed for efficient regenerators.
They might just break.
They can, yeah. And some materials, like the promising Laphase 13 family, undergo a significant volume change, like 1% during their magnetic transition. Doing that thousands, millions of times can lead to microcracking and fatigue. Basically, the material wears itself out. Corrosion can also be an issue for some materials in contact with the heat transfer fluid, so developing more ductile alloys, using protective coatings, and doing long-term durability testing are all crucial.
So materials are a big piece of the puzzle. What about the engineering side? Building the actual device.
Right, then you have the device engineering challenges. A major one is efficient magnetic field generation. We talked about the magnet options permanent, electro superconducting, getting a strong enough field that's uniform over the regenerator volume and that can be cycled rapidly and efficiently is tough and expensive.
Are there promising solutions being worked on for the magnets?
Yeah, people are working on smarter permanent magnet designs like those Hallback arrays that really concentrate the field where you need it. Also, hybrid systems, maybe using a permanent magnet for the base field and a small electromagnet to modulate it. And ongoing work to make superconducting magnets cheaper and less reliant on liquid helium cooling.
And getting the heat in and out efficiently. You mentioned the fluid flow.
Optimized heat transfer is critical. You need to get heat into the MCE material from the cold side and out of it on the hot side very quickly and with minimal losses. That whole temperature glide concept in the AMRR cycle is key, matching the fluid's temperature change to the material's temperature change along the regenerator bed. Get it wrong, and you lose efficiency fast. So designing optimal regenerator geometries, microchannels, packed beds, foams, and choosing the best heat transfer fluids are big engineering tasks.
And then just putting it all together reliably and affordably.
That's system integration and scaling. Taking a promising lab prototype and turning it into a mass-producible, reliable, compact, cost-effective product is a huge leap. It involves clever mechanical design, maybe using advanced manufacturing like 3D printing for complex parts, and developing sophisticated control system to optimize performance under real-world conditions.
Which leads back to cost, I guess. The upfront cost is still high compared to the fridges we have now?
Yes, that's a major economic and commercialization aspect. The initial cost, mainly due to the magnets and the specialized MCE materials, is currently higher than mature vapor compression technology. Plus, the supply chains for these new components aren't fully established yet.
So how do you overcome that?
The strategy is generally twofold. 1, keep driving down the cost of materials and manufacturing. 2, emphasize the long-term savings from higher energy efficiency and the environmental benefits. And initially, target markets where the unique advantages like ultra-low temperature, low vibration, or green credentials can justify a higher upfront price. Niche markets first, then hopefully broader adoption as costs come down.
Makes sense. What about the future of the research itself? Where are scientists looking for the next big breakthroughs in this field?
It's a really active area. One exciting direction is computational materials design, using supercomputers, AI, machine learning to screen thousands of potential compounds virtually, predicting their MCE properties before even making them in the lab. It massively speeds up the discovery process.
Designing materials on a computer first.
Cool. Yeah. Another area is exploring multicaloric materials. These are materials that show a thermal effect not just from a magnetic field, but maybe also from pressure, elasticaloric, or electric fields, electrocaloric. Combining effects could lead to even higher efficiencies or new types of devices.
What about making things smaller?
Definitely. Research into micro and nanoscale systems for things like cooling computer chips directly or tiny coolers for sensors. Also, integrating magnetic refrigeration with renewable energy sources is key for sustainability, designing systems that can work well with intermittent power from solar or wind, or maybe using waste heat as an energy source.
And still trying to crack that hysteresis problem.
Always, a deeper fundamental understanding of the physics behind phase transitions and hysteresis is crucial. If we can truly understand why it happens at a microscopic level, we might figure out better ways to control or eliminate it in those high-performance first-order materials.
Okay, so we've talked about the ideal properties and the challenges. Let's put some real names to these materials. You mentioned gadolinium as the benchmark. How do some of the other contenders stack up the ones that came after greed, trying to improve on it?
Right, let's look at a few key players. Gadolinium GA itself, as we said, is the classic benchmark. It's a second-order material, works near room temp. Its ESM and JetTad are decent, maybe 510 JGA and 2-3K for a couple of Tesla field change. But challenges are its high cost, being a rare earth, and its RCP isn't fantastic compared to newer materials.
So, good starting point, but room for improvement. Then came those colossal alloys.
Exactly. The GD-Sci alloys, like GD5, Sci2 GD4, these were a huge step up in performance, showing that giant MCE linked to the first-order magnetostructural transition. Peak ASM can be almost double that of GD, and ATAD significantly higher too. Huge cooling power potential.
But the downsides were.
Big ones. Significant thermal hysteresis, often 510 Kelvin, which really hurts efficiency in a cycle, and they tend to be quite brittle, making them difficult to manufacture into usable shapes. So, massive effect, but practical challenges.
What about trying to use less rare earth, maybe something cheaper?
That leads us to the Lefacii 13-based compounds, lanthanum, iron, silicon. These are very exciting because they use much less rare earth, just lanthanum, and show excellent MCE performance comparable to or even better than the GD-Sci alloys in some cases.
Also first order.
Yes, they have a first-order transition, often called a magneto-volume transition because the volume changes abruptly. You can tune the transition temperature quite easily by adjusting the composition. They can get ASM up to 20 GkG and ATAD around 5K for a moderate field, often with a higher RCP than SHIED. Very promising.
And the main challenge there.
The primary challenge is that inherent brittleness, which is directly linked to that large 1% volume change during the transition. Repeated cycling can cause cracking and fatigue. Making them durable is key.
Okay. Another family often mentioned is Heusler alloys. What's their story?
Heusler alloys, especially the nickel-manganese-based ones like Ni-M and In. Niemann on S. These are also very interesting because they undergo a different kind of first-order transition called a martensitic transition, which is strongly coupled to magnetism. They can show very large entropy changes, sometimes even larger than Lefacii 13.
Sounds great, but what's the catch with Heuslers?
Again, it's often hysteresis. Both thermal and magnetic hysteresis can be quite large in many Heusler alloys, which significantly reduces the reversible MCE, the part you can actually use for cooling cycles. Taming the hysteresis while keeping the large effect is the main game there.
Are there any other major classes worth mentioning, perhaps newer ones?
Sure. People also look at manganites and perovskites like LACA MnO3 compounds. They show MCE often linked to metal insulator transitions. They might offer a wider operating temperature range sometimes, but generally the peak MCE magnitude isn't quite as high as the best intermetallics. And then there are emerging classes like amorphous or nanocrystalline alloys, which might offer benefits like reduced hysteresis and better mechanical properties. Also, various transition metal compounds and even molecular or organic magnets are being explored, each with unique potential advantages for specific applications. The search is definitely broad.
Wow. Okay, so to wrap up this deep dive then, we've really journeyed through the science of the magnetocaloric effect, right from the basic physics to how it's measured.
Yeah, and we've seen the really compelling advantages it offers, getting rid of harmful refrigerants, the potential for much higher energy efficiency, and that quiet, vibration-free operation.
We also looked at how it works in practice with the AMRR cycle and just how crucial both the material science and the device engineering are to making this technology a reality, from finding the right stuff to building the machine around it.
Absolutely. And we've seen it's not a simple path. There are real challenges with materials performance, cost, durability, that pesky hysteresis, and with engineering the devices efficiently and affordably.
But the journey towards magnetic refrigeration being commonplace, it's definitely ongoing. The fundamental benefits, though, they seem really strong. It feels like it could genuinely lead to a paradigm shift in cooling, doesn't it?
It really does. So maybe let's leave you with this thought. Imagine a future where that constant background hum of your refrigerator just disappears,
Mm.
replaced by silence. Your air conditioner runs purely on magnetic force, and maybe our planet breathes just a little easier as a result. All thanks to this hidden thermal dance happening inside magnetic materials. What other problems, maybe ones we haven't even thought of, might this silent revolution end up solving?